Hello everyone, do you hear me?
Yes.
Good, thanks. So let's start. 1 second, let me just share screen here. So today we are going to discuss about Gaussian processes. As an alternative non-parametric method to do machine learning tasks. Okay, so first of all, let me try to motivate why this is like a very interesting model. So the motivation for this is the following. Well, there are several motivations, but imagine you take the linear basis function model, like you remember from the first lessons here. So you take a number of capital M functions, nonlinear functions. So you have this catalog of functions here. and you use this model in a Bayesian framework. We have in the one of the first lectures in Bayesian learning, we were deducing the obtaining the expressions for the posterior and the predictive distribution correspond to this model. So if you take this and then you take n, which is number of functions in your catalog, going to infinity under some mild conditions, the result of that is going to be a Gaussian process. So this is already telling you that it is a quite flexible. This GP that we are going to study today is a quite flexible model. And not only this, but more famous result on that. Imagine that you're still in the Bayesian framework, but now you embed a neural network in the Bayesian framework. I mean, we know how to build now neural networks, and I mean, don't be scared about Bayesian neural network name. This is just the fact that the output of the network is defining, if you want, the output of your data given some number of parameters, right? If I use cross entropy, etc., so the output is of the network is included in this likelihood, and imagine together with some prior over the parameters, then you will get the posterior, right? So this is just what I'm saying about Bayesian neural network. But imagine that you work in a Bayesian framework using a neural network as your model. And imagine that your neural network is just one hidden layer. One hidden layer neural network with age units in the hidden layer. So if you take age going to infinity, the resulting distribution, the distribution of the output is going to be a Gaussian process again. This is a famous result by Neil, I think in 1996. And actually, this result has been extended recently, when I say recently, like 4 years ago or so, by Google team about a deep network, not a simple shallow network like this one, but if you take a deep network in the limit of infinite number of units in the hidden layers of the network, then you obtain a Gaussian process. So this is a motivation. This is a motivation about flexibility, or if you want, expressiveness of this type of model. And this is typical. This is typical from non-parametric models. Why? Because you know that in non-parametric models, the complexity grows with the size of the data set. Okay. As we saw, for example, in nearest neighbors, or as we saw, for example, in kernel methods, let's say that the larger the data set, the more complex your model is. And in general, these non-parametric models are very, very flexible, let's say. Okay, so this is more or less, I think, an important motivation to study this model. So let's try to introduce them. So far, except previous lecture, which were about parametric, non-parametric models. So you remember that what in a parametric model, imagine that you have a data set like this one, where you have some points here. So in the parametric approach, just first of all, you assume some functional form for the distribution of your output. For example, we have assuming a lot the Gaussian, something like this, and then as a second step, you say that this function here is given by a machine learning model, let's say a linear basis function or neural net or whatever. So in the non-parametric approach, either this was relaxed, and that was the case of the previous lecture. So in non-parametric, previous lecture, relax the first condition, the first, let's say, step. And then we got either nearest neighbors or kernel models. And today, we are relaxing second step. So what we are doing in Gaussian processes is, in GPs, is first you do assume a particular distribution of your data, of your observable, Y in this case. And since it's Gaussian process, then the distribution is Gaussian. In general, this is a particular example of stochastic processes, or stochastic processes. Then, for example, Dirichlet processes. Then you assume that there's a Dirichlet distribution behind all the data, etc. So, but now the distribution is assumed to be Gaussian. But now, instead of proposing a function like this, this is not fixed now. Now the strategy is going to be the following. Let's be more like modest and content ourselves with knowing only the values of this function mean, fi is the values corresponding to xi at some finite number of points. So what I'm saying is, instead of fixing the functional shape of this, let me just say that I require that I know the values of the function at some specific points, right? So then, okay, let me just draw a plot here. So imagine I have this here, and then I have observations here, something like this. And then I just require the knowledge of this function in at these values of y. I mean, let's say that I have this y, but then I require that fi is equal to yi. And this is all I need. But then you see I have how many possibilities? I have an infinite amount of possibilities, because I can have a function which is just like this. I can have a function which is just like this. I can have functions in between, etc. Right? So I have an infinite amount of possibilities here. For the functions that satisfy all of them the requirement of passing through the training points, through the outputs, let's say. So in that sense, I can think of it in a similar way as I think of a random variable. So if I have a x, let me just not put x. If I have another variable set, if it's a random variable, I can sample from this random variable. In the very same way, let us think of this function as a random function. My task here is to have the distribution, to define the distribution over functions and not over variables. Okay, so I will have a mean function. Let me call it m, which is just the first moment of that distribution over functions I am trying to build. And I have a covariance function. The covariance of the function, which is just, I'm just applying the same definitions here that I applied for a random variable. Now I applied for a random function. Just put like this, and this, let me call it k of x and x prime. Then it is said that the function is a Gaussian process, and it is written like GP with mean function and covariance function. Analogously to the case where you have a variable, which is a random variable following a normal distribution or a Gaussian distribution, here you have our hypothesis here is that this function is a Gaussian process. But let me just go to the definition of that. So definition, a GP, a Gaussian process, is a collection of variables, of random variables, any finite number of which have a joint Gaussian distribution. Okay, so this is the definition of a GP, and for us in this case, our random variables are just the values of this function at the given points. This is in our case what the random what the Gaussian processes are. Okay. Oops, what did I do? Right. So, but let us be more concrete. So, what is our task? Our task is to let's say estimate a generating function, some data, right? This is in general in statistical inference. This is something I like to repeat always. So I have, imagine I have, just draw another plot here, x, y. Imagine I have the following situation. I have a point here, and I have a point here, and I have a point like, I don't know, here. And this point has x1, and here f1, x2, 2, 3, f3. So then we assume, let us assume that this function is smooth. Okay, in the sense that we are assuming some smoothness here that allow me to predict points in these ranges, in this range here. And then if I assume this this property of the function to be smooth, then I will need to build a covariance matrix, like somehow reflecting the similarity property among all the points, right? So the covariance matrix should somehow reflect some measure of similarity, in the sense that if a point x is close to point x prime is close to point x, then the output should be intuitively close to the output of x. In that sense, I am trying to implement the notion of smoothness, if you want. So in a way, what this translates to is to the fact that I could think of these values to be correlated, because they are close to each other. So there is some degree of correlation between them, right? And then imagine that if they are correlated, then let me put them, all of them. I have f1, f2, f3. Let me collect all of this in a vector. These 3 points, these 3 outputs here. I collect this in a vector, and then I declare that they are, well, I am using a GP hypothesis here, so they jointly follow a Gaussian distribution. Let me just assume for simplicity that the mean of this Gaussian distribution is 0, and this is the typical assumption in the literature, and that gives in general very good results. And then I need to specify somehow my correlation between these 3 variables. So take a look at the points x1 and x2. They are closer together than point x3, right? So somehow there is a stronger correlation, this is our hypothesis, from f1 and f2 than from f1 and f3, because points x1 and x2 are closer together than x1 and x3. So let me try to build here a covariance matrix. Of course, covariance matrix with the correct properties, reflecting the fact that points 1 and 2 are more correlated than point, for example, 1 and 3. So I put here 0.7, 0.2, but this should be a symmetric matrix. So I put here this. And then the correlation between point 2 and 3, well, it's probably smaller than correlation between 1 and 2, but larger than between 1 and 3. So let me just put here, I'm just putting random number, but just to reflect the fact that if I have a correlation matrix like this, then I would get, I would have expressed the similarity of this data set, in the sense that these 2 points are more correlated than these 2 points. Okay. By the way, this in the GP is called a kernel function. That's why I put a K above. So kernel function, and remember the last lectures where we saw a kernel. There is a relation. I mean, it is not it's just not a random name. It has to do with the kernel in the sense of the kernel function that we saw in the previous lecture. But let's not dig into that for a moment. Okay, so there are many kernel functions that you could build off. So one possible choice of a kernel function that implements this sort of behavior is actually one of the kernels we saw last lecture, which is just the square exponential, right? So here, xi minus xj square, where you know that if these two inputs, xi and xj, fall apart, are infinitely separated, then you get a 0, and if they are equal, then you get a 1, right? All right, so let me just copy this here in order to make another plot, but using the same right here. Right, so let's try to think about what would be the estimation of the output at a new point. Let me put the new point, I don't know, here. What would be the estimation of the output? Would that be here? What do you think? Here, or maybe here? What about this one? What about this one? So in our minds, we somehow, under this assumption of similarity, there is somehow I hope you share with me the notion that this is unlikely to be the output, and also this one, and that somehow the output should be in this region, right? Because we have assumed in the back of our minds, we have assumed this property of smoothness, right?
But it depends on the underlying function.
It depends on the underlying function, but if I have assumed smoothness, it would be weird to have something like this, right? Definitely, this is smoother than this one. given the lack of a data point in this region, under the assumption of a smoothness, it would be probably unlikely that that the point is either this or here, right? I have no clue of what is the value in this range because I have no observations in this range. Of course, it depends on the underlying function. But imagine that this underlying function, I haven't sampled the underlying function in a large region of input, then I need to assume something for that. Okay, so let's try to estimate under our hypothesis what would be the output. Let me put this output f star. F star is just f evaluated at x star. Okay, so let's evaluate f star given f, which is just a vector where I collected my 3 data points. So under this assumption of smoothness or that this or the Gaussian process, the idea is to put all of these guys together. So F1, F2, F3, and F star. I put these guys, all of them, together and declare that they follow multivariate Gaussian with 0 mean and some covariance matrix. So now let me write this covariance matrix in a blocked form. So I put here K, and I put here it's just a vector. This is just a point, right? So X star is just a 1 point in this case. So let me just write it, and then if you have a question, just tell me. And finally, a number here. So in this case, this would be 3 by 3. This is a scalar. This would be 1 by 3, 3 by 1. Okay, and 1 by 1. So I would have a 4-dimensional covariance matrix because I have 4 points. And then what I would like to compute is the following thing. I would like to compute, the aim is to compute P of F given the previous, given the observations, right? And in order to do that, let us write here a property. I don't know. So let me just open for a minute a parenthesis. This is just a parenthesis on the property of conditionals of Gaussian. So if I have, let me say a vector, F1, F2, Fn, right? And then I have that this vector follows multivariate Gaussian, in general having mu as mean and some covariance matrix here. Then the conditional, let me write the conditional like this. Imagine I have a conditional of the first k component given the rest of the components. Then this is going to be Gaussian. It's going to be Gaussian with the following mean. Let me write it like this: mean 1 given 2, and covariance matrix sigma 1 given 2, let's say, something like that. So the expression for that, obtaining the expression for that is in the very similar spirit to the homework of the first lecture, where you were trying to compute the conditional for the posterior given two Gaussians. But I'm just giving here the expression here, but it is quite similar to that. So let me just, before that, let me just pre-express this probability here in the following block form. Let me just re-express P of F given above to be the following: mu1 and mu2 corresponding to the two groups of variables, and again the covariance in a block form. Let me put here sigma 1 1, sigma 1 2, into 1, sigma 2 2. So if re-expressing this in this way, the expression for the conditional mean are this one. So this is mu1 plus sigma 1 2, sigma 2 2 minus 1, f2 minus mu2. So f2 is what let me put this f2, and this is f1. And again, doing the same, a similar game as for that exercise. I have the expression for the covariance. 1 2 2 2 2 minus 1, sigma 2 1. Okay, just take this as a theorem or as given, and so let me just put this an expression. I will use it later. Sorry, but the message I wanted you to take home is that there is an expression defining the Gaussian distribution of a conditional given given a joint Gaussian like this one. Okay, so let me just close the parenthesis here. And then with the above property, by using the above, I can go back to my task here. My task is to obtain the probability of F star given the observations that I have collected in an F vector. And then applying this formula, I just get that this is of course a Gaussian. So let me just put the first moment or the mean is written like this. Then applying expression 1, this is just k star vector transpose k minus 1 f. This is by applying this one, because remember that I have assumed 0 means for the prior, so this term goes away. This term goes away. So I have only this. And the variance of this point is, now I take this expression here, applied to 1 point. So this is k star star. This is just a number here, right? This is this quantity here, k star star, and minus the same as before. K minus 1, and then K star vector. Okay, so this result here is nothing but the mean and variance of a point in the test. Let me call it test set. A new point. So let me go back to my figure. I will take again this figure. Oh, I probably pasted. What if I just paste this again? Okay, but a little bit smaller. So what I'm saying is that I have now for X star, I may have a prediction, for example, lying here, and then I may have some idea of the uncertainty of this prediction, as usual in Bayesian models, as this one, right? So you get your mean and your uncertainty of the prediction. But now imagine, and now I tell you, okay, go and do this and repeat the same for many values of X star. So many values of X star, then I go, and then I make a grid, a fine grid, as fine as I want. And I repeat exactly the same thing. And if I repeat exactly the same thing here, for example, imagine I have a point here. If I have a point here, I may have here a prediction, which is, I don't know, here, and then I have my uncertainty, or here, and then I have also my uncertainty, etc., right? And by doing this fine grid, I will be able to just draw here what would be, do again, what would be the mean. So this would be the mean function. And by joining all these uncertainties, imagine I'm here just plotting the one standard deviation, if you want. Then I can obtain something like this one. Like this. And then similarly like this. Or this is, for example, this is the standard deviation. One standard deviation, for example. This is just a cartoon, right? So why why this standard deviation is behaving like this? Because remember that I have to require the functions to all of them to pass through the training point, so they shrink at the training points, and then far from the training points they go wider. And you remember that from Bayesian learning, from the lecture of Bayesian learning, was exactly the same thing. So we have a precise prediction closer to the training points and a less precise prediction far from the training points. So in that way, even though I am being modest and I am saying, okay, I only require to know the function at some specific value, then by doing this procedure and making a grid as fine as I want, then I am essentially having, in practical terms, I'm having a function, right? Because in any case, in computer, this is what you need to do. You need to define a function, you plot it by defining a grid, right? So in practice, you do have a function, which of all the values of your grid. Is there any question so far?
So Brian, I do have a question. So in principle, this procedure looks very nice if if you try to look in between your points, because you can essentially check more or less if the smoothness works. But let's say if you want to extrapolate this function outside the domain, there are like no warnings, because I mean you can, as you show in your picture, take up or take down after the last point, and then you don't really know, right?
At least this is a modest, sorry, not a modest, an honest output, because no matter what model you choose in statistics, you should be less confident if you are extrapolating. And at least this implementation, as well as any implementation in Bayesian learning, tells you that watch out, here the uncertainty is growing like crazy because you are actually far away from a point. Of course, you don't know. It can be anything. You don't have observations to support your prejudice. But at least you are having a measure of uncertainty, which you don't have, for example, with a traditional neural network.
And Brian, is there any way of accounting for the uncertainty of the measure points, like the black points? I mean, if you
yes,
know the uncertainty.
we will see it in some minutes. I mean,
Okay.
The black points, they are usually noisy. They come with uncertainties coming from your measurement, etc. Yes,
Okay.
we will just see how to do it in a second.
Okay, thank you.
But yeah. So Jose, did I answer your question?
Yes, you did.
Okay. So let us summarize the idea, just to be a practical summary, if you want. So the first idea, in order to implement this, is to propose a GP prior. And the proposal of a GP prior comes by first create a grid of points, of inputs, right? And this is, say, endpoints. And then once you have created the grid, you follow for example, the square exponential kernel, and you can compute the matrix, the covariance matrix K, which is n by n. This is your covariance matrix. And you compute this with the elements square exponential that for example, this one that I wrote above. And then you can get values of the function, or if you want, you can sample the function, sample functions from the prior. So the values of the function I'm talking about is fi, which is just evaluated at xi. So you sample f from your normal, your multivariate Gaussian, which, as I was presenting above, has zero mean and some covariance k, because this is your prior, right? So by sampling a function, so when it is important to understand this, when I say I sample a function, it is in practical terms the same thing as sampling from a multivariate Gaussian, because I'm saying that a function is equivalent to give the values of the function at different inputs, right? So what I'm trying to pass here as a message is that this is defining a function, because this is a vector collecting all of these guys. So in practical terms, this is just a function. And this is just the GP idea. So, and then you need to sample from this. How do you do this in practice? Let me just open another small parenthesis here. So how to do this? How to do this sampling? Let me just go first for a univariate, for a single Gaussian. So if f follows, if a variable f follows Gaussian with the mean mu and variance sigma square, then sampling from this, is the same as sampling from this mu plus sigma times the standard normal. Okay, so you get exactly the same type of samples, the same samples. If you sample directly from this, giving, I don't know, a library or something, or doing this procedure. So this is the idea for a single variable, but for multivariate Gaussian, there's an analogous procedure. So imagine that I have a multivariate Gaussian, so a multivariate or a random vector following a multivariate Gaussian like this. Then the idea is to compute like the square root here. Here, this is the variance. Sorry, something happened. I don't know. Do you hear me?
Yes, no problem.
Okay, so you hear me, but I don't. I don't know why. I got spilled from the. I have two accounts, so let me just. Okay, I will solve this problem in the break, which is in some minutes. So let me just continue here. What I'm saying is that in a similar way as you go from a variance here, and then you need to, by doing this trick, what you require is the square root of the variance, which is a standard deviation. So what is the standard deviation now here, or the measure of a square root of a matrix, of a covariance matrix? This is just, this is just the so-called Cholesky decomposition. So the Cholesky decomposition, where this is a real lower triangular matrix with positive diagonal entries. Okay. And by doing this Cholesky decomposition, you can sample from the multivariate Gaussian. From this multivariate Gaussian, you can sample in a similar way as above. So you just add to the mean vector L times a standard multivariate normal, if you want. Okay. So let me now show this in a code, but for showing this in a code, I need to connect my computer, which somehow was disconnected. Let me just give me 1 second. Is there any question so far? I mean, I'm just opening my browser again. Let me try again. There is a problem with the network here, with the Wi-Fi. Okay, so it seems I'm in. Let me share screen then. Come. Do you see my screen?
Yes.
Okay, so let me just, before the break, just implement this idea in code, which is very simple. So imagine, well, I have this, as usual, Jupyter notebook here, and I am defining some, imagine I have this data set. So this data set is coming from just a sinus function. Okay, and I have, I don't know how many, I have 6 points or something. Okay, so imagine I have this data set, and the procedure is the following. So I just create, first of all, a grid of points. So let me choose, I don't know, 50 points or something like that. Okay, and then I have my grid. Then I build the GP. So for building the Gaussian process, I need to define this kernel function. And the way to define this matrix that I was commenting you before, it is implemented essentially with the 2 lines. Bandwidth here is a hyperparameter that we will see later, but essentially here we will just set it to 1. So it's just 1 over, I mean, exponential of the square distance divided by 2, where square distance is just a 1-line function here, and A and B are arrays like this one. Okay. I don't know, you can convince yourself that this is, later I will give you the notebook, of course, but this is actually computing the matrix. But once I have this, what I need to do is to well, compute my covariance. The covariance matrix of the function values at the test point. So I just apply the function to the kernel function to the test points to my grid, actually. So it's just computing the covariance of the test with respect to itself, or the variance, if you want. And then I apply the Kolesky decomposition here by applying it to this one. Note that I have added here some very small constant here, but this is just for numerical stability of the function. Anyways, what I wanted to show you is that once I have my covariance matrix, and I have my Kolesky, my matrix L from the Kolesky decomposition, I can plot the number I want of functions. For example, let me plot 10 prior functions. So the prior is going to be just mu, but mu is 0, so this term is not entering, plus L times a multivariate normal, standard normal. Okay, and then the size of the dimension of the multivariate normal is the number of points, and I want n samples of objects from that. So I have 10 objects. So in general, this is given as an output an array of 50, which is the number of data points I have in my grid of points. 50 by 10, because I have 10 values. So if you picture this in this way, and then I plot it, I plot each of these 10 samples, what I get is this. So each of these lines is a function, right? So it is just one of these 10 results that I obtain from that. And this is a prior, so there is no observations there. If I haven't fixed the random seed here, so if I do this again, give me another 10 random functions like this, etc. Right? And then I can plot how many functions I want. I can plot 100 functions. I don't know. You see, there is absolutely no structure here because I haven't observed any data yet. This is just a prior over functions, and the prior over functions, they can be whatever. The only thing that you may extract from this is that these prior functions have 0 mean, which is my assumption. And now, after the break, we are going to see how the behavior of these functions is affected by the observation of the data. In other words, what we are trying to get in the second part of the lecture is to implement the conditional of f star given the values of the function at the observed data points. Okay, but let us do a 10-minute break, and we come back at 12:10. Is it okay for you? Do you hear me, or I was offline?
Yes, I can hear you. Yeah.
Okay, so let's do this break until the 12:10.
Okay.
Thanks. Okay, let us continue. Do you hear me now?
Yes.
Yep.
Okay, thanks a lot. So now, so at this point, what we have is just some prior over functions. So some functions that they are random, right? They have no structure at all. And now what we need to do is to compute the posterior given the observations, right? Okay, so by following the procedure shown above, it's just a summary, right? So what we need to do is to build the Gaussian joint. So build the Gaussian joint. Let me just say, okay, I have my observations here. This is my vector of observation. And this is, let me now assume I have a number of points in my test data. So this is my predictions for test data of size. Let me take, I have m points in my test data, and then those are my observations, and there are n of them. Okay, so so what I need to do is to say, okay, I have a multivariate Gaussian with 0 here, and you know, this is a vector of n zeros, and this is a vector of m zeros, right? And then I have the covariance matrix written in block form, where I have this is n by n. Then I have another matrix here, which is forget about this one. And this is n by m. And this one is just a transpose of this one, which is m by n. And finally, I have the covariance matrix of the test points with themselves, which is, of course, m by m. So I have, in general, this multivariate Gaussian with dimension n plus m. And then I just apply the expressions that you saw above to get the conditional. So if I apply these expressions, then I get, let me write like this, f, the mean of this collection of predictions, given my observations, is just applying just the same formula, k star transpose the inverse of k times y. Let me just rename this as new star. And then the covariance is just k star star minus a term similar to the above, but multiplied instead by k star. So I can build this. If I call this to be just sigma star, then what I need to do is to do the Koleski decomposition of this. that I will call as a result of which I get the matrix L star. And then finally, what I need to do is to draw predictions. But draw a prediction, so I have an F star, a function, one sample of the function of the posterior. So this is just a sample S. And there will be n samples of them, so 10, 100, whatever you want. And this is just mu star, I mean this, this vector here, plus L star times a noise vector, where the noise vector is just a number sample, or a vector, sorry, sample from a standard multivariate Gaussian. This is as simple as that. And so let us now go back to the notebook and see the rest of it. Right, so what I'm doing in the rest of the notebook is just to implement this formula. But first of all, I need to obtain the block matrix, right, of the prediction. So the first block is K, which is the covariance matrix between X train with itself, and KS, which is the covariance matrix between X train and X test. So when I do this, I can now build the mean of the predictive of the posterior, which is just written by that. So this is just the multiplication of K star transpose times the inverse of K times the vector of observations, and the variance K star star minus K star transpose times inverse of K star. And I just want to have the standard deviation of it. So I take the square root of this result and I plot it. So when I plot this, let me just take again 10 samples. Then I need to define this L star. I just put L here, but it's so the Cholesky function, the Cholesky matrix, sorry, L, which is just the decomposition of the predictive variance. And I do exactly the same I did for the prior. Just to remember, the prior here was like this. Now I do have a mean which is non-zero. This is given by mu. Mu is just this one, plus L times a vector, which is just a sample from a random standard normal, multivariate normal of size of dimension n, and I want 10 samples for that, or how many I want, okay? And the result is this one. So you see here that what I'm plotting here, first of all, the training points in blue. These blue squares here. Then I plot all the 10 functions here. So those are these functions with thin lines. And just to be illustrative, I just plot here the area covered by 2 standard deviations. So this is mu minus 2 standard deviations mu plus 2 standard deviations. And then just plot this shaded region covering 2 standard deviations, where standard deviations is just the square root of the predictive variance. And then I get this, which is more or less showing the same features that I was drawing before in that cartoon, in the sense that you are very precise around training points, but then when you go away from the training points, you are just less precise, right? And if you are extrapolating, then you are way less precise. Okay. But this is the sort of plot which was very similar to the one in the previous, in the first lectures about Bayesian learning. So this is exactly the same type of prediction, the behavior of the prediction obtained for a linear basis function in a Bayesian framework. It is just that now I have a much more flexible model. Is there any questions regarding this final treatment here? Okay, so let us then continue. So note that here, let me just stop sharing and then go back to my notebook, to my notes. Sorry. Okay, so what we have done so far, so this is just the basic procedure of GP for regression, and a final thing to mention in the context of in this context is the fact that so the kernel function in general may have hyperparameters. So we have been using a very simple exponential, but in general, kernel function may look like this. So I have like an overall prefactor times my square exponential with some bandwidth, and that was the bandwidth that you saw in the notebook, in the Jupyter notebook, times x minus x prime square. Okay, so these guys here are hyperparameters, and these hyperparameters you need to a priori should be optimized, right? But the choice of the hyperparameters, it matters, right? Because depending on the hyperparameters, the predictions will be smoother. Predictions will be smoother or not, or less smooth, depending on these parameters here. So let me just show a picture here. Just let me see, where is it? This. Let me put it here. So this is, by the way, taken from a book of Rasmussen and et al. So this lecture is partially prepared from this book, which is called Gaussian Processes for Machine Learning. This is like the standard literature, the standard textbook of Gaussian processes. And Rasmussen is like a guru in this community. Okay, so what I'm saying here is that so depending on the hyperparameters, you may choose you may obtain as a result some in smoother or less smooth prediction. So here, for example, you have the case where the hyperparameters were there were coinciding with the hyperparameters defining the data. So data, if you want, was generated artificially from a Gaussian process with some hyperparameters, and if you use them exactly for making a prediction, imagine that you knew the true values of the hyperparameters, then that is the prediction here. And here the result of a prediction of a predictive distribution, where actually the bandwidth, this denominator here, is smaller than the one that you should have used. And then you see that the predictive distribution is, and I think that also this value is larger in this plot. So you see what is the effect of that, no? So that the points in between, these points in between, they have a larger uncertainty and more noisy, right? And this is a result of a smoothing parameter which is larger than the one that you should have used. So you see that the effect of that is actually to get a mean which is not quite passing through all the, or capturing, if you want, the real behavior of the data. So your prediction, your predictive distribution is just too smooth. It's just too, it has too low variance. So you may think of it as an underfitting of your data if you want. Okay, so the message here is that you should somehow learn these hyperparameters, right? And the way you do this is by, so you should learn the correct values of the hyperparameters. And in general, in the literature, in the community of Gaussian processes, what people do is what I've been telling you to do previously in the context of Bayesian learning, which is comparing the two models are compared using the marginal likelihood or the evidence. So you just compute the evidence as a function of the hyperparameters. Okay. So if you want to maximize the evidence as a function of the hyperparameters, okay? In the Bayes theorem, is just the denominator of your Bayes theorem, of your expression, right? But I am not entering into this because this is well, in the case of regression, well, this is straightforward in the sense that it is Gaussian as well. So you have a Gaussian marginal likelihood or evidence, and you can just easily maximize it. Okay. Okay, that's all for regression. Let me just discuss now classification. Oh, no, so before discussing classification, what I forgot to discuss is the procedure where you include the noise, and that was one of the questions before, the procedure where you include the noise of the data. So in general, you have noisy data. So noisy data that coming from some function that underlying function here that you just are trying to estimate. And this noise may be either coming from your observations, or let me, for simplicity, say that this is independent and identically distributed data coming all from whose noise is just a zero mean and standard deviation sigma square. So I have the same uncertainty sigma square for all the points. This is just an assumption, but it doesn't have to. It's just for simplicity, but the algorithm is exactly the same. The procedure is exactly the same. So in order to take this into account, the prior covariance is changed as this. So so now my prior is the same Gaussian with zero mean, but now the covariance, you just add it. You just add this, right? So the sigma squared times the identity matrix. And if you have, instead of a unit of a identically distributed data, you have data where all points have a different uncertainty, or which is another way to call it is heteroscedastic data, then you just change this part, right? So this may be, for example, a diagonal matrix with sigma 1, sigma 2, etc., right? Okay, so now this is the prior and the predictions. Also change as, so the mean of the predictive, the change is straightforward. You just need to add to k, you need to add just this term. And the covariance is just minus k star transpose k plus sigma square minus 1. Sorry. And in that way, you can you will get predictions which do not go exactly through the training points, but they have a, there is a width, there is a minimum uncertainty of the predictive distribution at the training points given by this term. Okay. So let us now go for classification. Is there any question so far? Okay. So let me just review for 1 second the basics of classification in Bayesian framework. So remember, in classification, we are after this object. So this is the conditional. This is the probability of the some class CK given some input, where my output is categorical, right? So then I have the likelihood. The likelihood was my data, or if you want, of the this categorical output was just, for example, this, or the log of this was the cross entropy, right? I W TIK, where TIK is the 1 to k, or 1 hot encoding of the labels, if you want, the true label. So for a chosen prior, then propose a prior, and then you can just compute the posterior then. Applying the base theorem, right? I have the likelihood, I have the prior, I can compute the posterior a priori. The predictive distribution, which is the probability of some class here given some new input of the test point, let's say. Some new test point x star, and given the data I have observed, this is the training data, then this is just the marginalization over all the parameters of your model of ck given the input and the weights or the parameters of your model times, I mean, the posterior, right? So remember, this is just the output of your classifier. Output of a classifier of a probabilistic classifier in the sense of, for example, logistic regression, neural network, a naive Bayes, all of these models, right? So the procedure in GP, in the Gaussian process, the procedure is to simply, I mean, you remember that in GP you have these predictions here, and these predictions, they are just real predictions from minus infinity to infinity, right? So in general, those are predictions in the real axis. But now the idea here is I don't want a prediction which is from minus infinity to infinity. Since I want this to be a probabilistic model, I would like a prediction to be in the range 0, 1, because I need to give a sense of probability for that. And in order to do that, the idea is to sort of squash fi in a bounded function with a bounded function. For example, I just put whatever I have as a result of my GP, I put it as an argument of a sigmoid. And then you know that the sigmoid is just bounded between 0 and 1, right? And this is interpreted as, in binary classification, at least, this is interpreted as the probability of class 1 given some data in binary classification. So this is just a trick here to go from an unbounded prediction to a prediction which is in the range 0, 1. However, by doing this, actually, the very presence of this squashing procedure actually complicates substantially the whole implementation, since now the predictive is the following. It's now more complicated. So imagine I am still in the case of a binary classification. So the probability that the output is class 1, given some new input, and given the training data, call it like that, this is just the integral over this squashing function times the posterior of this value and then you need to marginalize over it. Okay, so think of this f as the latent variable in a similar way as you have weights or parameters in your neural network or any other model that you need to marginalize in order to get a predictive distribution. These values f star are also parameters of your model or latent variables of your model that you need to marginalize in order to get your predicted distribution. However, what is this object here? This posterior. This is again an integral where you are integrating the conditional that we used before. So this guy here is the conditional, the Gaussian conditional, as we saw above, using that formulas, right? So this object is very easy. This is just a Gaussian. And now the thing is that you do have to marginalize over all the functions, all the values of the function at the training data, right? So this, if you want, is the posterior of f, these latent variables, this latent function at the training data. So you apply the Bayes theorem. You say, okay, the posterior, then applying the Bayes theorem is just this part. This is my observation, right? Let me just put here y, because x is given. So the inputs are given. So the data, the only random part of the data is the output. So let me just put it like this, times the prior. So this is the prior we are familiarized with, the GP prior. You know how to build it. I just gave you a recipe for that. This divided by just the evidence. So this guy here is complicated because this guy here is a non-Gaussian likelihood. This is the likelihood, which is non-Gaussian. We are now dealing with the categorical variable, so we cannot have a Gaussian. We cannot have a Gaussian distribution for it. So there are several choices of likelihood in the literature. A common choice is the following. Common choice of likelihood. Let me just put the log of the likelihood of a point I with output yi given some latent variable at this point is the minus log of 1 plus e to the minus yi fi. I mean, just note that this is the same as saying that this is just a sigmoid function. So this is just sigmoid like this. So you remember that in the lecture of classification, probably it was, that for generative models, you could always express this as a sigmoid. I think it is probably lecture 4 or something. Yeah. So you remember in lecture 4, in the probabilistic generative approach, that I could, for two classes,
I can't hear you, Brian. Someone can hear Brian.
Me neither.
Do you see my screen or not? Sorry. We are now dealing with the categorical variables, so we cannot have a.
We don't see the screen, but we
Do you hear me now?
Yeah, yeah. We hear you, but the screen is not. I mean, you're not sharing it. I don't know. I don't see it.
Do you hear me now?
Yes, yes.
Yes.
Yeah. So I think Wi-Fi again gave some problem. Let me share. I don't know where I stopped sharing. Where did you stop? Here?
You were talking about lecture 4 and noting the formulas. I think that's when I stopped hearing you.
No. Okay. So I was just saying that from lecture 4, the message was that you could always express these sort of functionals in terms of a sigmoid, because in lecture 4 we saw it in the generative models. We saw that for a binary classification, you could always express, okay, the base theorem is this one. I hope you remember that. And you can just rearrange the whole expression to be a sigmoid of some argument, and the specific form of the argument is not important here, but it's just the message is that you could always express this as a sigmoid if you want. So this is something that is not unexpected, but there is also it also has some reasonable properties, and this is what I wanted to discuss now. So this choice of likelihood is reasonable because of the following. Imagine that the label of your point is class +1, and that has a prediction of your GP, of your Gaussian process. You have a very large value of f. So now you go here, so you see this is e to the minus infinity. So this goes away, and the probability. So this probability I tends to 1. So then you have a high likelihood. So this high probability, right? So high likelihood, which is good because you are by squashing a function from minus infinity to infinity, by squashing it from 0 to 1, you know that the plus infinity corresponds to 1. So this is what you should get for making a correct prediction. And now what would happen if instead of the true label of the point being class 1, it is -1, and now let me go to this parameterization of a binary classification where classes are -1 and 1. So if you instead you have -1 here together with this infinity here, then actually this exponent here is positive. So that means that this p is going to tend to 0, right? So you have a very low probability or low likelihood. And the opposite, if as a result of my prediction I get a very large value of f but negative, then here you will have instead that p tends to 0, and this is reasonable because my correct prediction is 1, but here p tends to 1 because my correct prediction is -1. Okay. So this is like a reasonable choice. For multi-class classification, this is all binary. For multi-class classification, instead of having one latent function, so I have the latent function is just this vector f1, etc., fn, where n is the number of data points. Instead of this, I have one latent function per class, and there are k classes. So I have something like this, one of these vectors per class, where k goes from 1 to capital K. Okay, so I have if you want, a matrix of latent variables, f, which is f11, f12, f1k. So this is all the observations. Sorry, what? All the predictions for my k classes. All the predictions. So the prediction of the first point for the k classes, the prediction of the second point for the k classes, etc. N1, N2, and k. So this is a bit ugly in that sense, in the sense that now for every point of your parameter space, of your data point, for every one of your data points, you have k values to determine from your training, and these at least they are assumed to be uncorrelated. So there is no the covariance matrix, the joint covariance matrix, if you want, is diagonal, and a popular likelihood for that is the following. Oops. So in the same way as binary took a likelihood which was sigmoid, then here intuitively you have a likelihood which is a softmax. Which is just f I k prime, right? So this is a softmax. This is consistent with the fact of consistent with that lecture on classification, where the probabilistic models typically assume softmax for multi-class classification. However, this is not the unique choice. This is not the only choice. So another choice, which is a bit more drastic, and it's not a smooth, but it gives good results, is the following. The probability of yik given fi. Fi, remember that fi is the vector of k components. So I am here for the data point I have capital K latent variables that I collect here in a vector. And the same here. And this is just the multiplication over k prime different from k of a step function fik minus fik prime. So essentially here, this will be 1 if fik is larger than all the rest, and 0 otherwise. But this is another choice in the literature that people use and that give good results. The idea here is that if you make the correct prediction, then this probability is larger than if you don't make the correct prediction, which you have here, but you also have here. So then the whole point here is that you need to maximize if you want. Sorry, you need to predict to estimate this this object here. This should be estimated in order to compute this, because you need to make a prediction. You need to make this prediction, so it depends on this, and this depends on this. And as I was trying to convince you now, is that this guy here is non-Gaussian, because the likelihood is non-Gaussian. And what is happening is that not only non-Gaussian, but this is interactable. And this is intractable here. Let me just put a y here to be consistent. And this is intractable here because of the non-Gaussian likelihood, which makes this evidence to be intractable as well. And then there is the whole discussion about how do you estimate this guy, either by Monte Carlo methods, sampling methods, like the hybrid Monte Carlo, or by variational inference, or by Laplace approximation, many methods, okay? But this is not the moment to enter into this discussion. But okay, I think I will stop here. Is there any question on the lecture? Do you hear me at least?
Yeah, we do.
Okay. So this is more or less what I wanted to say about Gaussian processes. There is much more to say, but I have no time. Like a connection between this and the linear basis functions via these kernels. So there is a lot of nice features on these models that you can check in this book at the Rasmussen. So one thing that I would like you to do, I know I haven't uploaded the last material yet, but I will hopefully do it today. One thing I would like you to do is to take the notebook and play with the, like, implement, if you want, the hyperparameters in that function. Let me just go for a second to share the screen.
Well, One question in the topic of homework. When was the we had to do everything and send it to you tomorrow?
Ideally, yeah, tomorrow would be the deadline, but I can give you, I don't know, the rest of the week if you want.
Okay.
Yeah.
Okay.
It's not very strict on that, but I should give you some deadline. So let us give till Friday.
Okay, fantastic.
So the idea of this homework would be to play with this, to implement hyperparameters here. Here there is already the hyperparameter of the width, of the bandwidth, and so you should play with that in order to see the behavior of how does it change the behavior of this predictive distribution, but also to include the overall normalization. So which means it was like a prefactor here. So it was a prefactor here. And that changes the amplitude of the kernel. So you would like to, I mean, I would like you to play with this.
Also, Brian,
Yes.
can you define a list of the homework as you have done for the first 2 days?
Yeah. So okay, I will send an email with the summary of all the homework so far.
Fantastic.
Thanks.
Yeah. So. Okay, so if not other issue or thing to mention, let's close here and then let's meet tomorrow for the final lecture.
Okay, fantastic. Thank you very much.
Bye.